So we're going to have a start and look at magnetism, which is our next topic in our unit on fields. Magnetism has a lot of similarities with electric fields, so a lot of this won't seem that new. So what we've written here is we wrote that magnetism was first described by a Greek named Thales about 500 BC. He wrote about a rock that came from the town of Magnesia, which he named Magnetis or Magnesian rock. Rocks bearing these properties would be known as lodestone. Geologically, we call that magnetite, a mineral rich in iron 3 oxide. As the elements in this rock aligned themselves, it was observed that the rock was attracted to certain materials. Magnets form two poles or dipoles, called a north pole or a south pole. Unlike electric charge, magnetism can only exist as a dipole. So if you take a magnet and break it into two, you are going to end up with two smaller magnets, each with their own north and south pole. Whereas in electric fields, we had positive charges or negative charges, but we didn't need to have both to have an electric field. Whereas in magnetism, we need to have a north and a south pole. The other thing about magnets is that they don't discharge when they're touched. Like an electric charge is built up. If it is grounded, then the charge dissipates and all the charge is spread back out. It's a lot easier to study magnetism because magnets don't discharge. Just like electric fields, magnets follow the inverse square relationship, so the force of magnetic attraction or repulsion is proportional to 1 over the distance squared. Generally, the rules that we come into grade 12 with are that like poles repel each other. So north repels north, south repels south. Unlike poles attract each other, and the force of attraction varies inversely as the square of the distance between two poles. In a non-magnetic material, atoms or domains are randomly arranged in magnetic materials. The domains are mostly aligned. So if we could picture a random object where we have atoms or domains randomly aligned, the material would be considered essentially non-magnetic. We can take a magnet and rub the magnet in the object in the same direction over and over again. And what will happen is the domains inside that object will align with each other. And when that happens, we get what we call a temporary magnet. You can do that with the blades of scissors. You can do it with a lot of different metal objects, and the magnetism will remain slightly but very quickly be lost. When there is no magnetic field present and the magnetic properties remain and relatively as strong as they were to start with, we have what we call a permanent magnet. One of the things about magnets we need to realize, and it becomes relevant if you've had an electric motor that's run for a long time and just stopped working, is that if a magnet is heated, the strength of its magnetism will actually weaken. But if you cool it back down, it should work again. So using an electric motor, if you run it for a long period of time, the motor will become less strong, especially if it's not being cooled properly. But when the motor cools back down, it should work like it used to, unless there was some sort of melting or something involved. If the magnet is heated beyond a certain point, the magnetic properties might be completely destroyed permanently. This point is called the Curie point. The Curie point is known for many materials. So for example, iron is 770 degrees Celsius. Beyond that temperature, the magnetic properties of iron can be destroyed. Cobalt and nickel are also given. A lot of magnetism we find to be quite similar when compared to other electric fields, as we've already stated. So the big thing is the differences. Electric charge is easily transmitted through conductors. Magnetism is not. Almost anything can be given an electric charge, but not everything can become magnetic. And electric charge, as we've already stated, can be monopoles, but magnetic must be dipoles. So what we want to do here right now is we just want to have a little look at what magnetic fields can do. So I'm not sure how well this will show up on the camera, but we will try. So these are iron filings in a solution. And as you see, I can put in a magnetic object, and you can clearly see the field lines forming. The light from the camera is obviously interfering a little bit, but you can see that the poles have the maximum amount of force, or the maximum amount of magnetism. We talk about the maximum amount of force of the field lines per square area as something called magnetic flux. We don't really talk that much about it in our course. The neat part comes when we want to look at attraction. We're going to kind of look at this, and we can draw it in a little bit later. So I've kind of redistributed them. I have two magnets here. So I have two like poles. It doesn't matter if they're north or north. Sorry, two unlike poles. It doesn't matter if they're north, north, or south, south. So there we have two magnets that are going to go together. So what I'm going to do is I'm going to put them in, but not let them touch. I'm going to slide them out so we can kind of see what's happening. And as you can see, there is clear field lines. Some sort of exchange between those two poles, where the magnetic lines actually go from one to another. And if I let them touch, it makes it really obvious. I don't know if we can actually see that any better. As we kind of pull it up, there's a nice little view. So what we're seeing, and you can see it sort of changing as I let them touch each other, is you're seeing that the fields are interacting, and they definitely want to come together. Let's redistribute my little iron filings again, and let's look at repulsion. So I'm going to put those two in, and we're just going to see what happens. Now the big thing I want us to notice is look at the iron filings between the two heads of the magnets. They almost go straight out. There is absolutely no interest in these two touching. So the area between the two magnets is also almost becoming void completely of any of the filings. The filings that are directly right where my finger is are kind of going straight up and straight down. And as soon as I let it go, the magnets push each other apart, and you can kind of see this exaggerated, where the space in between is completely cleared. So we can sort of simplify this with a drawing. We have north, we have south, and for simplicity's sake, we have north and we have north. So field lines will leave north and go to south. Whereas in the repulsion model, there was almost a line in between where field lines, and again I have both north poles, so I'm going to draw the field lines going away from it. Field lines can't cross. You can sort of simplify this. This is much better seen in person when you actually get a chance to play around with the magnetic field and see exactly what's being created. So that takes us to a little bit more on magnetism. So in 1819, Danish physicist Hans Ørsted was demonstrating the heating effects of electric current in wire when he noticed that a magnetic compass would align themselves relative to the wire. He noticed that when he turned the circuit on or closed the circuit, the needles of the compass were deflected at right angles to the conductor. Ørsted had discovered the basic concept behind electromagnetism. So I have a wire here. This is sort of the general principle of what he did. Basically what he had done is he ran a wire. And he took a compass. Just a general compass. Sorry, when we have a magnetic demo set right next to the camera because it's deflecting quite a bit. But what he discovered is that when current was placed through an electric wire, what he actually saw is he saw the needle deflecting. And when he saw that deflection, he realized there was some sort of connection between electricity and magnetism. We came to know that moving electric fields or moving electric charge created a magnetic field if that charge was moving through a conductor. And it was a really big discovery because that is one of the principles we use in a lot of different fields. So there's a couple things we'd use to try and figure out direction. As you can tell, it's very difficult to determine what is north and what is south. So I don't know exactly what our background in electric fields is, or electric currents, but we're going to assume, first of all, that electric current is the flow of positive charge. Some people talk about electric current as the flow of negative charge. In the physics that we do, we generally assume a positive charge and base our rules around that. Everything, if it was a negative charge that we're dealing with, what we're about to do, everything is sort of backwards. So it's sort of important to remember that. So basically what he came up with was that if you had a coil of wire, or just not a coil of wire, just a straight wire, and you could put your thumb in the direction of which way the current was flowing. So let's assume that I have positive and negative in this diagram. So positive charge is going to flow away from the positive, and you put your thumb in the direction the current is flowing. So positive charges will flow from the positive up to the negative. Then the magnetic field forms in a way that it curls with your finger. So in this diagram, the magnetic field is going to curl with your fingers. If we take the battery and we flip its charge, my thumb would go down and it would curl the other way. So this is called the first right-hand rule, and it's used to determine the direction of the field lines in on a conductor carrying electrical current. So we can kind of extend this idea to the idea of a solenoid. Basically what that is it is a simple closely wound helix of wire. So there's a little plastic thing in the middle here. What will happen in this case, because the current is moving in a really tight circle, the field will be intensified. And we can create a relatively big magnetic field, that can almost replicate a bar magnet. And I guess depending on the amount of wire you use, you can definitely overpower the standard bar magnet and create an electromagnet if you put an iron core or something in the middle here. So all a solenoid is, really, for our intents and purposes, is a wound helix of wire. That's all we're really focused on. So that brings us to right-hand rule 2. It says, how does the magnetic polarity of a coil or solenoid relate to the direction of current in the coils? Basically, it allows us to find the north pole of a magnet. So once again, we have positive and negative. It's got to be the direction the current is flowing. You got to focus on that as well. And as you can see, the wire is wrapped from behind, and it's kind of coming around. So every time it goes around, it comes back up, goes around, it comes back up, goes around, and comes back up. So you take your fingers and you wrap them in the direction of the wrapping relative to the direction the current's flowing, and your thumb will always point to the North Pole. So it is really that simple. It's just a way of us determining which way is north, and we just call it the second right-hand rule. So basically, it's this idea. You can see the coil is wrapped. I put my fingers in direction of the wrapping. My thumb will point to the north end of the electromagnet if I put a metal core inside here. Now, we're starting to figure out that magnets can work with electricity. They're not really, they're interconnected topics. So what this demonstration does is it looks at exactly how a magnetic field, how a compass can be deflected using what we call a tangent galvanometer. Let's see if we can get one of those into the picture here. So it's really this device here. It's there's terminals that allow us to attach different lengths of wire. What we do is we put a compass on the little pedestal in the middle, and by applying current to this, the needle will deflect. So I'm going to try and simulate this a little bit without hooking up the wires. So what we do is we align it while the current is off to north, usually is what I do. And then as we turn the current on, the needle will deflect as the magnetic field becomes stronger and stronger. And it will actually maximize to the point where the compass inside the center of this will actually be at a right angle to the wrapping of the coil. So that's all a tangent galvanometer is. Just get focused back down here. So when we do this experiment, I'm just going to use some data that we've created. What we find is it's directly proportional. And these are degree deflections and how far the compass is actually deflected. And this is a measure of the currents going through the coil. Normally, we can kind of predict what's going to happen. And what we will see is a perfect linear relationship. So what that actually tells us is that the amount of current in a coil is proportional to the magnetic field. and directly proportional because it seems to be if I double the current from 100 to 200, the deflection goes from 10 to 20. That all deals with right-hand rule 2. The question we ask ourselves after the demonstration is, it says, is the deflection needle directly proportional to the current? Yes. And I'm going to write it is linear. So according to Newton's third law of motion, for every action there is an equal and opposite reaction. If the current in a conductor caused a magnetic field that exerted a force on a magnet, then a magnet must interact with the magnetic field from the current to exert a force. So that means there must be a force being generated. So that brings us to right-hand rule 3. So here's my conductor, positive terminal, negative terminal, and current flowing through it. The right-hand rule works this way. You put your direction in the way that the charge is moving, the positive charge. You put your finger lines in the direction of the field line, so this would be north and south. And when you do that, the force will come perpendicular out of your palm. So if the charge was moving downward, I would have my fingers in the same direction, my thumb going down, and the magnetic force will be pushing into the page. It really seems to help us figure out exactly where things are going to move, and it can be a very useful force. The fact that we can use an electric current flowing through a wire to generate a force in a magnetic field is the principle behind electric motors. So we call this the motor effect. So as always, we like to quantify this. We like to be able to figure out exactly how strong this force will be. So when a conductor carries a current through a magnetic field, several factors affect the size of the force exerted on the conductor. First, the magnitude of the magnetic field, which is going to be signified by B, and it is a vector, and it's going to be measured in Tesla, is directly proportional to the strength of the force as well as the amount of current, intensity, or amperes. Electric current is represented by the letter I. Finally, the length of the wire or conductor passing through the field is directly proportional to the strength of the force. So when we put that together, we get the magnetic force is equal to the strength of the magnetic field times the intensity of the electric current times the length of the wire. So this is going to be in meters, amps, and Tesla. The SI unit for magnetic field is the Tesla, but you'll also see Gauss with a capital G being identified, and it's 10,000 Gauss per every 1 Tesla. Now, it would be too easy if it was just that equation multiplying 3 things together. So we do have a relationship here where we can actually look at the sine of the angle. So, for example, if the current is not flowing directly perpendicular to the magnetic field, that's something that we've got to take into account. So the current is going through the magnetic field. Well, the magnetic field is on a right angle. So what that means is only the perpendicular part will actually matter. So if I resolve this B into its horizontal component, and I have the angle, then the sine of the angle will give me the perpendicular part of this situation, which is where this comes from. So it's the sine of the angle, again, drawn like this. The sine of the angle times the magnetic field strength will give us the perpendicular field lines to the current and allow us to calculate directly. The part that is parallel to the current, which depending on exactly which reference point you're using, I'm going to use vertical or J in this direction just for right now. The adjacent side of this unit vector basically shows us that the parallel magnetic force does not generate a force. So the parallel magnetic field does not generate a force with the current going across that magnetic field. So let's actually see how we can do. It says a length of straight conductor carries a current of 4.8 amps into the page at right angles from the magnetic field. The length of the conductor that lies in the magnetic field is 25 centimeters. If this conductor experiences a force of 0.60 newtons, what is the magnetic field intensity in Tesla? So first of all, into the page we can represent with x's. Out of the pages we'll use zeros. So I have a magnetic field, picture a vector going into each one of those lines. And a wire carrying a current is passing through the field. So obviously if the field is coming straight up, it is at a right angle with that field, with that current. So we have F equals BIL, F equals, we're going to solve for magnetic field. So IL equals B. Or more commonly written, magnetic field intensity is equal to F over IL. B equals 0.60 newtons divided by we'll do length first, I guess, 25 meters times 4.8 amps. And the unit will come out in Tesla. Or 5,000 Gauss. The last part that I really want to talk about is just how this applies to a DC motor. So here we go, we got positive charge and negative charge. So we got current flowing in, current flowing out. So the first thing is that we have magnets, a north pole and a south pole. So realize we have field lines going across here. We have a conductor lying through that magnetic field with current going up into the up and around the circle, I guess, through clockwise. A couple of little things about this. This thing here is called a commutator. Specifically, you'll see the break here. This is called a split ring. A split ring commutator, which is going to give us the DC. DC stands for direct current. Basically, the current will always flow in the same direction, and because this is split, that allows that to happen. The alternative is AC, which is alternating current, where you don't see the split, and the commutator is a little bit different, but the current will constantly switch direction. So DC is generally thought of as the type of electricity you see in batteries. And AC is usually what comes out of the wall socket in your house. So we can apply the right-hand rule to this. So I have current going this way. I have magnetic field lines going this way. So I put my fingers in the direction of the magnetic field. I turn my hand so my thumb is pointing in the direction of the field of the charge. And what will end up happening is the force will end up coming out of my hand. So this means the force, let's write that in just a different color to make it stand out a little bit better. The magnetic force is going to force this to go up. When I do it on this side, put my hand in the direction of the magnetic field lines, my thumb in the direction of the charge, you can see it going down and away. it's going to be coming into the page. So what will happen, because this is able to rotate, is this side of wire will be forced up, this side will be forced down, causing the ring to flip. When it flips, the brushes, which are attached to the commutator, will cause the current to reestablish in the clockwise direction, and at all times on this DC motor, one side the force will be up and one will be down, so this will just keep on spinning. So a really simple look at what that means. I don't have my brushes on here, but there's two sides to it, one for AC, one for DC. Here's my commutator. You'll notice that it's conductor, then it's broken. So as it comes in, one side gets forced down and one side gets forced up. But then because this is broken, the charge stays in the same direction and the coil will continue to spin. And while it continues to spin, we can obviously have an axle or a belt attached to this, and that will allow us to do work with it or do something useful with that motor. And that's what we call the generator principle. So we know that force is proportional to electric current, the magnetic field, and the length of wire in the field. We can also have a quick look here at how this applies to just a charge. So imagine we had a magnetic field. So it's just magnetic field, North Pole, South Pole. And imagine I had some charge. Let's make it something really simple. +1 microcoulomb charge. And let's assume this charge is moving through here at some velocity. And we'll make the velocity 650 meters per second for fun. Now, the first part of this equation that we see up here, it says force is equal to the strength of the charge. Again, you'll notice it's absolute valued, times the speed the charge is moving, times the intensity of the magnetic field. So let's just use the same magnetic field we had earlier at 0.5 Tesla. So we can simply calculate the force. Force is equal to charge times the velocity the charge is moving times the strength of the magnetic field. So force is equal to 1.0 times 10 to the negative 6 coulombs, 650 meters per second, 0.5 Tesla. It's at a right angle, so it would be sine of 90, which is not really worth writing out. So 1 exponent 6 negative times 650 meters per second. The force is 3.25 times 10 to the negative 4. Use our right-hand rule. So I'm going to rotate the page so I don't have to dislocate my wrist. But here's the field lines. Thumb in the direction of the positive charge. Keyword, positive charge. The force would be going out of my palm. So the force will be going into the page. Charge, field lines, positive, it comes out of my palm. So that is essentially how that works. Please note that a negative charge has the opposite direction. That's the main idea there. So let's do a bit of practice. I have a couple questions here that we can go through and see what we actually picked up through that little discussion on magnetism. It says particle 1, which has a charge of 3.6 times 10 to the negative 6 coulombs, or 3.6 microcoulombs, and a speed of 862 meters per second, travels at right angles to a uniform magnetic field. This has got to be charge 1 because it's going at a right angle. The magnetic force it experiences is 4.25 times 10 to the negative 3 newtons. Particle 2 with a charge of 53 microcoulombs has a speed of 1,300 meters per second and moves at an angle of 55 degrees relative to the same magnetic field. So both charges are positive. That will be helpful for us. So we have this equation, F equals B QV sine theta. I think I have written it out before as QVB, but it's the same equation. So B then, therefore, is equal to F over the magnitude of the charge times the velocity the charge is moving times the sine of the angle. So our first approach is to get the strength of the magnetic field. So B is, we're going to use the first charge to do that. Over the magnitude, so 3.6. Remember to go into coulombs. Don't leave it as microcoulombs. 862 meters per second. We're gonna try and do this 4.25 exponent 3 negative divided by 3.6 exponent 6 negative. It's 1.37 Tesla. So we now know what the strength of the magnetic field is. Now we want to know now that we know what the magnetic field is, so 1.37 Tesla, we can actually calculate the force on the second charge. So F equals, let's write it out the same way as we did before. So force is equal to the magnitude of charge 2, which is 53 microcoulombs, times the speed, times the magnetic field intensity that we just got, times the sine of the angle. So make sure we're in degrees. 53 exponent negative 6 times 1,300 times 1.37 times 55 sine. The force is 0.0773 newtons. Finally, we're going to do something similar again. It says, at what angle relative to the magnetic field would particle 2 have to move so that the magnetic force experienced was 0.0500 newtons? So we'll start with the same equation. I know the force I want, I know the charge, I know the speed, assuming it's the same speed, and I know the field intensity. So sine of the angle will be equal to force over Q V B. The sine of the angle would be equal to 0.0500 newtons over 53 times 10 to the negative 6. Assuming it's still going 1300 meters per second. And assuming the same magnetic field strength. So let's calculate that out. 0.05 divided by the charge times 1300. That's 1.37. So let's call it 32 degrees relative to the field. So those are pretty similar questions, pretty standard questions on magnetic force quantitatively. A copper rod that is 0.150 meters long with a mass of 0.0500 kilograms is suspended from two thin flexible wires, as shown in the diagram. At right angles to the rod is a uniform magnetic field of 0.500 Tesla pointing into the page. Find the direction and magnitude of the electric current needed to levitate the copper rod. So, first thing we have to do is determine the direction, and that's fairly easy. We know the field lines are going into the page. So if I put my right-hand rule, put my fingers into the page, if my thumb is pointed to the left, then the force will be coming out of my palm down. So because I want that vector to go up the page, the current must be going to the right. And again, you can verify that with the right-hand rule. So for A, I'm just going to write to the right. For B, we know the weight of the rod, so we can calculate that. So the mass of the rod times gravity we know that the weight needs to equal the magnetic force. And this is perpendicular, so we know magnetic force is equal to FBIL. So 0.4905 newtons. The magnetic field intensity is 0.5. The current is what we're trying to solve, and the length of wire that's in it, it's already in meters. So I is equal to 0.4905 divided by 0.5 times 0.15 equals 6.54 amps. So we know the magnitude of the current and the direction, so it's got to be to the right. And I is equal to, I have 3 significant digits, so 6.54 amps is okay. And that's basically all of our calculations that we need to worry about in magnetism. At this point, if we know how to do these types of calculations on the first page, we know how to apply the right-hand rule to solve problems, and ultimately know how to explain how a electric motor works, a DC motor specifically, we should be okay.